Good morning. Sorry it took me so long to get logged in. My computer would not log in. Let's see. Make sure we got everybody logged in. Let's see. I think Keely's trying to get in. So let's see. We're missing Alec. Well, it says Keely's trying to get in. Let's see if we can get her in. And then I think let me send. I think like maybe linked in with the old one. Let me send a message to him real quick. Well, I guess Keely's connection's having trouble because she popped out. Okay, so what we'll do is just for a few minutes, I know that I sent some notes kind of late last night. So if you haven't had a chance to print those out, if you can either just pull them up on your computer or if you get a chance to print them out, that would be great. What I've decided to do is go ahead and start giving y'all some note sheets for each section. And then that way, you don't have to write your notes anymore on the homework. We'll just start doing our notes on our sheet in class. It also has your assignment on there. So then that way, you've got a better way of keeping up with the notes for the class, the assignment for the class, and then hopefully that'll be kind of a little more organized way that I can kind of help you guys. And then that'll also serve as like your study sheet to prep for the test, to be able to look back at and things like that. So hopefully everybody was able to get those. If you have any trouble with it, be sure to let me know and I'll be happy to, text it or re-email it or whatever you need me to do. But like I said, I thought that might be a little bit easier way for you to kind of follow along. You can see that there's places where you have to fill in the blanks. And also it kind of helps you to know what is the most important information from each section. So anyway, with that being said, I hope everybody had a great break. It looks like my internet may be lagging a little bit, but anyway, I hope everybody had a good break. I know that it went by way too fast for me, as I'm sure it did for you as well. But one of the things to be thinking about is as quickly as this whole first semester has gone by. Good morning, Alec. So as quickly as this first semester went by, second semester is probably going to go even faster than first semester did. So it has a tendency to kind of the second semester, let's see, try Keely again. Second semester has a tendency to go a little faster than first semester, but because we have, we've got several breaks that we have going on. Dog, get out of there. My dog's tangled up in my cords under my table. Get out, come here. Come out. Get out from under my cord. Come here. Come out. You're wrapped up. Hang on just a minute. Come out. What have you done? Just a second. Would you come out of there? There you go. Okay, now step over this way. There we go. All right. Sorry. Okay. So that's why I was really kind of thinking over the break about what was going to be the best way for us to kind of go forward. And I know we have the shift and how we did all the homework stuff, and you guys have done a great job with picking up with that new format and everything. So I was trying to think about how can I make it easier on you guys, but have y'all still be able to get the content better, but have the notes. So that's why I've decided to go ahead and start those note sheets for each section. So I will be, when we're in at the co-op, I will be giving you a chapter packet. So when we join back next or week after next, I will actually give you the packet. You won't have to worry about printing it out and all that stuff. But for right now, I'll just send you a page at a time to have prepared for the next class. So I will be sending this afternoon, I will send you guys the pages for tomorrow. But like I said, that'll kind of help you guys to go ahead and have the notes on a piece of paper. You'll have the assignments written down so you'll know what is due and all that good stuff. Okay.
I have one question.
Sure.
Whenever we go back to class, like 2 week, wait, I
Uh-huh.
guess, yeah, 2 weeks from now, do we have to bring anything?
So what you'll do is when we come back to class, you will bring these notes that were the notes and the assignments for chapter 7.
Okay.
Okay, so from now on, what we'll do is your notes will count on the page that I sent you, and then whatever assignments that you're working on that go along with the notes, you'll bring those in. Okay. All righty, so we'll go ahead and I'm going to share my screen real quick so we can go ahead and take a look at those and kind of talk about it. And hang on just a second. Let's see. Geometry. Let's see. All righty. So like I said, this will be kind of what it looks like. Why is there that big old gap in between? I don't know what happened there. That's strange. It like, you know what it may be, because may just be the way it loaded into my Notability. I probably need to save it as a PDF before I load it to Notability. Okay, so as you can see, the top of it will be labeled for which section it goes along with. And then I have made it to where it goes in order. Okay, so it's going to follow right along with the text. Now, there may be some things here or there that some little things that I've added in that's not necessarily word for word in the textbook. So when I get there, I'll be sure to tell you. Y'all know how I like to throw in just little things that help me to remember something or an extra little note about something that I think will help you. So anyway, so there may be some blanks in there that'll be where it's information that I give you that it's not necessarily directly from the text. Or it may be that I reworded it or reordered the sentence because sometimes it'll have like a definition and then the word it's defining is at the end, and sometimes I'm putting the word at the beginning. So, but know that it's going to go in order. So as you're going through this, we'll fill in a blank as we get to that information. So with that being said, we are starting with chapter 7 today. So go ahead and turn to section 7.1 in your book if you're not already there. And then, so think about where we wrapped up with chapter 6. In chapter 6, we had a lot dealing with different shapes, different quadrilaterals, different parallelograms, looking at our different formulas for area, perimeter, all that good stuff. So we're kind of, obviously some of those things are going to still come into play as we move forward, but we're kind of shifting gears a little bit with this new section and talking about how our different shapes that we've been learning about, how they, this whole chapter is dealing with transformations. Okay, so we're looking at how our original shape that we're starting with can change positions, can change locations, how it can, turn or flip or things like that. So at the end of algebra last year, at least if you were in my class, we did just a quick little geometry wrap up at the end of the year where we talked about rotations and reflections and slides and things like that. And so that's what we're looking at. That's what we're kind of starting with today. So so if you have your sheet, let's see, I'm going to go ahead and pull up the chapter. And actually, probably what I need to do real quick on my computer, I'm going to pull up that sheet. Because let's see. Give me just a sec. Okay, while that's pulling up, we'll go ahead and take a look. And it says, what's this chapter about? Chapter 7 is about transformations. Transformations describe how geometric figures of the same shape are related to one another. So the big key there is, of the same shape. And so we're just looking at those different ways. So there we go. I can have that open and see it on here. Okay. All right, so we are going to move along. So remember, looking kind of for just a minute at the are you ready for the chapter skill review, distance formula. So again, remember I talked about how there are going to be certain formulas and things like that that you need to go ahead and commit to memory. Distance formula is going to be one of those. Distance formula, midpoint, all that good stuff. There's going to be certain things that that you just need to go ahead and commit to memory if you have not. So let's keep on moving. All right, so 7.1, rigid motion in a plane. Identifying transformations is our first goal. So it says figures in a plane can be reflected, rotated, or translated to produce new figures. The new figure is called the image. An original figure is called the pre-image. The operation that maps or moves the pre-image onto the image is called a transformation. All right, so let's go ahead and look at that first part of our lesson notes. Figures in a plane can be reflected, rotated, or translated, okay, to produce new figures. So if you have your note sheet, you're filling in those blanks. And then it says to produce new figures called, the new figure is called the image, and the original figure is called the pre-image. Okay, so we're using the same word for both of them, image and pre-image, but just remember, obviously with the word pre, that's going to be the first one. So my original is called the pre-image, and then whatever movement or change has been made is called the image. Okay. And it says a transformation is the operation that blanks or moves the pre-image onto the image. So the word there is maps. The word maps is what we're using. Maps and moves is going to be used interchangeably. Okay, so when we talk about how it started at one point and then changes to another, we're calling that it maps or it moves. And then it says, in this chapter, you will learn about 3 basic transformations: reflections, rotations, and translations, and a combination of these. So that's going to be our next one, where it says our basic types of transformations, 3 basic transformations. We said those are going to be reflections, rotations, and translations. And so we're going to be looking more specifically at each of those.
What's the second note? The transformation is the operation that blank
Maps or moves. Is that what you're talking about, where it says maps or moves the
Yes, ma'am.
pre-image onto the image? All right. So notice we've got our pictures underneath. So we can see where we've got these different pictures, and we can see a reflection of the line. So when you think about a reflection, think about a mirror image, okay? So we've got whatever that line is. If we're looking at a mirror, then we've got that, you know, that place between us and the mirror where things are flipped, okay? Everything is reversed from one to the other. So we can see where it's basically kind of, if we moved it and we flipped it right over that line, it's kind of got the opposite of everything, okay? Then the next one, hang on a minute. Let me see what my dog has got. She's eating pencils. Hang on just a moment. Dog, give me the pencil. What have you done? You've made a mess. She's giving me fits today. So yeah, she loves mechanical pencils, and this one, my son left somewhere, and she has just chewed it to pieces. All righty. Maybe we can get through class without the dog doing anything else today. I think it's too cold to put her outside, but anyway, all righty. So reflection, it has that mirror image, it flips back and forth, okay? Then one in the middle is talking about a rotation about a point. So if you think about whatever that shape is, if you think about it connected to a point and it just kind of goes around that point. So at any given place in the location, you can kind of see how it's shifting, and you can kind of see that arrow as it's showing that it would just kind of rotate or revolve around a point. So depending on where it is, you can kind of see. So obviously if it's going to be straight up and down, then it's going to be totally upside down in the opposite direction. So a rotation is where it just turns, okay? So basically when we think about a reflection, we're talking about it's flipping. A rotation is where it's turning. And then a translation. We can see where a translation, my F started and all it did was kind of slide over, okay? So we can also call a translation a slide. It just looks like it slid from one side to the other. It didn't turn, it didn't flip, it just slid, okay? So everything's still in the same direction. Nothing has changed with that. So those are going to be the 3 things that we're talking about. Now, right underneath that is our next little bit of information. It says some transformations involve labels. When you name an image, take the corresponding point of the pre-image and add a prime symbol. For example, if the pre-image is A, then the image is A prime. So that prime symbol, it looks kind of like an apostrophe. And so then I read it as A prime. So basically my original or my pre-image would be A, and then my image we call A prime. So I know it started out as A, but I know it's made some kind of change that's made it a little bit different, okay? So that's how I can tell the difference between the pre-image and the image, is because one is labeled A and one is labeled A prime. Okay, so when we look at our note sheet on there, It says some transformations involve labels. It just says it basically, I think I did this one exactly like it said. And so it says to add a prime symbol, okay? When you name an image, take the corresponding point of the pre-image and add a prime symbol. We read that as A prime, okay? Now moving on down to example 1, naming transformations. It says use the graph of the transformation at the right. And letter A says name and describe the transformation. So the first thing that I want to do is I want to look at my picture. And I can see that I still have a B at the top and then I have B prime. But then when I look down here and I look at A, I notice that in my transformation, A is not still in the same location, okay? So I know if it's not in the same location, I can rule out a translation. It didn't just slide. I know it's made some kind of turn, okay? It's either turned or flipped or done something. And so since I see A is over there and A is here and C is here and C is here, I can see that it has reflected over that line. Okay, so I can see that this is a reflection and it has reflected over the y-axis. So typically when we look at a reflection, we're going to try to figure out, so sometimes we can see that that line of reflection here is the y-axis. Now sometimes you'll have something in the top and then the bottom and you can see where it's reflected over the x-axis, but in this situation, we can see that we have triangle ABC and that it has flipped over or it has reflected over the y-axis, okay? So now it says, letter B, name the coordinates of the vertices of the image. Okay, so I'm gonna erase where I've marked and I'm gonna look at letter A, okay? So letter A, I started out at 1, 2, 3, 4, 1. This was my original, was 4, 1. But now when I look at my translation, I'm at 1, whoop, I said 4, 1, negative 4, 1. And over here, I'm at 1, 2, 3, 4, 1. So notice where I started at negative 4, 1, when it flipped or when it reflected over that line, my X value became positive and my Y value stayed the same. Okay, let's look at letter B. In letter B, we've got 1, 2, 3, negative 3, 1, 2, 3, 4, 5. So I'm at negative 3, 5. When I look at my reflection, I'm at 1, 2, 3, 1, 2, 3, 4, 5. So again, X became positive, and then we have Y, stays the same. Letter C, I start out with negative 1, 1, and with my reflection, I'm at 1, 1. So we can see that reflection over the y-axis just changes my X values. My Y's are staying exactly the same, but I have taken the opposite X values. And then letter C says, is triangle ABC congruent to its image? And so remember the word congruent means that it is equal to, okay, or measures the same. That means that each of my lengths are exactly the same of each side of my triangle. And so yes, that is true. And so it says one way to show this would be to use the distance formula. So if I wanted to make sure, I could use my distance formula and plug that in to show that each length stays the same after it has reflected. Or I can then I can use the side congruence postulate, showing that the three sides are congruent to the three sides of the image. So the pre-image is congruent to the image. Okay. On the next page, we have a new word, and it says an isometry. Isometry is a transformation that preserves lengths. Okay, so an isometry is a transformation that preserves lengths. Isometries also preserve angle measures, parallel lines, and distances between points. And then transformations that are isometries are called rigid transformations. So if we look at this, the next couple of points, an isometry is a transformation that preserves lengths, angle measures, parallel lines, and distances between points. An isometry is a transformation that preserves lengths, angle measures, parallel lines, and distances between points. Transformations that are isometries are called rigid transformations. Rigid transformations is the next point. So we're going to look at that in example 2. All right, in example 2, it says, which of the following transformations appear to be isometries? So remember, we just said that with an isometry, it's going to stay exactly the same no matter if it flips or turns or slides, whatever it does, everything is staying congruent. Okay, my lengths are staying the same, my angle measures are staying the same. If something was parallel in the image, in the pre-image, it's going to be parallel in the image. If I have just a certain distance between 2 points in the pre-image, it's going to be exactly the same in the image there. So if we look at letter A, we have a pre-image and the image, and we can see that they appear to be the exact same length for each side. So it does appear to be an isometry, and it says the blue parallelogram is reflected in a line to produce a congruent red parallelogram. Letter B, we have the blue pre-image and then the red image. Now, these do appear to be in the same shape, but they do not appear to be the same size. So that means the lengths of each side are different. So this is not an isometry because it's not congruent, because the lengths of my sides do not appear to be exactly the same. In letter C, we can see where we started with our image. We started with our pre-image, which is the blue. So we started with the blue, and we can see where it has started to rotate about that point, and we can see where it has shifted up. So it's just kind of swung up, but it still appears to be exactly the same. So it is an isometry because it is congruent. Okay, any questions about that? Basically, when I'm talking about a rigid transformation, we're talking about an isometry. That means it's exactly congruent. Nothing about the shape changes. Same length, same angle measures, distance between points, all that good stuff. It's just in a different location because it either flipped or it turned or it slid. Okay.
What was
Now
the
then,
last blank? I think I missed that one.
Are you talking about the last one right before where it says draw?
Yeah.
We haven't gotten there yet.
Okay.
We just finished up transformations or isometries. Transformations that are isometries are called rigid transformations. We're getting ready to get to the next section where it talks about mappings. Okay. So remember a moment ago, we talked about how the word map and the word move means the same thing. So if we say a mapping of something, it's where we can look at the pre-image to the image, and that's the movement that it has taken to go from one to the other. Okay. And so it says you can describe the transformation in the diagram by writing triangle ABC is mapped onto triangle DEF. So we can see where we started with the blue triangle. It has just slid and it is now mapped on top of DEF. And so it says you can use the arrow notation as follows. So I can write that as triangle ABC is mapped onto triangle DEF. And it says the order in which the vertices are listed specifies the correspondence. So remember when we were talking about different shapes and things like that, and we talked about how naming it is very important because, especially when we're looking at two different shapes, because we want to look at that correspondence here. So when I look at this, I can see that A corresponds with D, B corresponds with E, C corresponds with F. Okay, so we have to make sure that we put everything in the right location so we can make sure that we have done that correctly. So our next blank says in a plane, an isometry is a transformation that maps every segment to a congruent segment. Blank is a transformation of a pre-image onto another congruent or similar image. So that word there is mapping. Okay, mapping. And then the next thing says, draw the example of mapping from page 397. So go ahead and look at that example where we have the blue triangle ABC, where it transforms to the red triangle. So you'll just draw your triangle ABC, draw your arrow. So basically you're drawing this image right here. And below that, I want you to go ahead and write triangle ABC is mapped to triangle DEF. So I want you to go ahead and write down that visual image on your note page. And now we're going to look at example 3. I'll give you a minute to finish that up. All right, so in example 3, it says preserving length and angle measure. In the diagram, triangle PQR is mapped onto triangle XYZ. So we can see, obviously, hopefully you've kind of picked up on the point where when you see two shapes and they're connected with a line that has a dot and it looks like it's, we can see that that's going to be a rotation about a point. So that's going to be a key or something that when you see that dot there, you automatically know it's a rotation because they're showing you where it started and where it has moved to, and they're showing you that point where it has rotated about. So it says that triangle PQR is mapped onto triangle XYZ. The mapping is a rotation. Given that triangle PQR is mapped onto triangle XYZ is an isometry, and so we need to find the length of XY and the measure of angle Z. Okay, so what we're going to do is if we know that, looking at our picture, if we know that this is a rotation, what I'm doing is I'm looking to see what are my corresponding sides. Okay, so I'm going to go ahead and underneath it, I'll go ahead and write triangle X, Y, Z. Oh, let's see, PQR, I did that backwards. PQR is mapped onto triangle X, Y, Z. Okay, so looking at that order, I know which points correspond with which points. So I can see that P and X correspond. So I can see that these two are the same points, just in different locations. I can see that Q corresponds with Y. Okay, so in my blue and triangle PQR, I can see that the length of that side is 3. Therefore, I know that the length of side XY is also 3. Okay, so understanding the movement, understanding the correlation between the points, I can look at my pre-image and see that within my image, I can look at my length. Okay. Now it says, not only do I need to find the length of XY, I need to find the measure of angle Z. So again, because R corresponds with Z, and I can see that angle R is 35 degrees, then angle Z is also 35 degrees. Any questions about that? The main thing about looking at how my pre-image maps to my image, how that movement goes, and looking to see the main thing is we've got to pay attention to those corresponding points. Making sure that my points are corresponding will help me to transfer the information from the pre-image to the image, because remember, we're talking about an isometry here. So whatever my measurements are for my pre-image, my measurements will be exactly the same for the image. Okay. Let's go ahead and turn the page to example 4, and it says using translations or transformations in real life. So talking about carpentry, all right, so carpentry is definitely something where we see repeats and patterns. And so it says you are assembling pieces of wood to complete a railing for your porch. The finished railing should resemble the one below. Now, I don't know about you guys, but this is a fairly intricate railing. But if somebody was going to do that, that is fantastic. But I can see that it would be kind of difficult to make sure that everything is exactly the same. So it says, how are pieces 1 and 2 related? So if we focus in on pieces 1 and 2, notice that piece 1, my arc, my curve is at the top, and piece 2, it's at the bottom. So what kind of movement would this be? From 1 to 2, is it a reflection, a rotation, or a translation?
Rotation.
It's going to be a rotation, because we could see if this was, let's see, if I drew my little point and my little circle, I don't know. Anyway, you could see where if it started in one place, it kind of rotates around. It kind of moves around in that direction, okay? We can see that it's not a mirror image. It didn't just mirror image, and it didn't mirror image from top to bottom either. It didn't flip from side to side or from top to bottom. And so I can see where it has actually turned there, okay? So what about pieces 3 and 4? Look at 3 and 4. What kind of I'm sorry?
Reflection.
We have a reflection there. I can see where, you know, the line helps me to see that, knowing that I've got that line that it is reflected over, but then I can also see that it's just flipped, okay? It's just flipped right over. So here we have a rotation and a reflection. So it says, in order to assemble the rail as shown, explain why you need to know how the pieces are related. And so thinking about, you know, knowing the relation of the pieces will help you as far as like making sure that you've got the railing straight. And so that's why when we have those rotations and reflections, we want to make sure that each part is exactly the same measure, because you don't want it to be out of whack, okay? So that's a real life example, is using carpentry. All right, example 5, using transformations, building a kayak. Many plans for kayaks show the layout and dimensions for only half of the kayak. A plan of the top view of a kayak is shown. So if we saw this, obviously we would need both sides of my kayak to be complete to be able to make it work. So it says, what type of transformation can a builder use to visualize plans for the entire body of the kayak? So if I'm wanting my kayak to be exactly the same on the other side, then I'm having to do, and that's terrible. Let's see. Whoop. Obviously, it's not going to be exactly the same, but what kind of transformation am I using here to visualize it?
Reflection.
We've got a reflection again, okay? So again, we can see that in this measurement here, it has 10 inches. So I know that over here, this would be 10 inches as well, okay? So whatever my measurements are for one side of it, I know that the measures are gonna be the same because it's an isometry. And so I know it's got to be exactly the same, okay? So now we are to the guided practice. So a short little section. So it says an operation that maps a pre-image onto an image is called, what is this whole section about? When I map an image onto a pre-image, this is a transformation. Okay, we're talking about transformations. We talked about our main 3 different types of transformations: reflections, rotations, and translations. Okay, let's look at number 2. This section says we want to use always, sometimes, or never. So it says the pre-image and the image of a transformation are always, sometimes, or never congruent. Now, one of the things I want you to think about here is it's talking about a transformation. So if you look back for just a minute on page 397, example 2. 397, example 2 at the top of the page, were all of those transformations isometries? They were not all isometries, so they weren't all congruent. So are pre-images and images always, sometimes, or never congruent?
Sometimes.
Sometimes. Good. Yeah. So when we're talking about a transformation, sometimes they're congruent. If they are congruent, it's an isometry. If they're not congruent, then it's not an isometry. Okay. So number 3 says a transformation that is an isometry always, sometimes, or never preserves length. That one's going to be always. An isometry, a transformation that is an isometry always preserves the length. Number 4, an isometry always, sometimes, or never maps an acute triangle onto an obtuse triangle.
Sometimes.
So think about an isometry. Think about an isometry. That means it's exactly congruent. If I'm mapping and I'm going from an acute angle, so if we go back to example 3 on page 397, if I went back to to example 3, if I was mapping this figure, and it's an isometry, could I map angle R to angle Y? I can't, can I? Because it has to say exactly the same. It's got to have the same angle measures. So since an isometry preserves angle measure, I could not go from an acute to an obtuse. So that one is going to be never. An isometry never maps an acute to an obtuse because the angle measures have to be preserved if it's an isometry. All right, so now we got some pickup trucks and we're telling what type of transformation we have. Remember, our options for transformations are going to be reflections, rotations, translations. So look at number 5. Is this going to be a translation, a reflection, or a rotation? So basically, when I look at this, it's still facing in the same direction. Nothing has changed, right? Now, if this was a reflection, if this was my line, and it was, then what would my car would be upside down, or it would change directions. Okay, so basically this one, it just slid. And if it just looks like it slid down, if it's exactly the same direction, it's exactly the same direction from top to bottom and from left to right, then it looks like it just slid down. So if it just slides down, that's called a translation. Okay, because it did not rotate. Well, I mean, it didn't rotate and it didn't reflect over a line. Looking at number 6. Okay, so I can see that if this was my line, if I had a line there, it looks like it just flipped right over the line, doesn't it? And so my flip is called a reflection. And then number 7, I can see where it looks like where it has flipped, but notice this one's going in this direction and this one's going in this direction. If we look at number 6, my trucks are still going in the same direction, just one's upside down. So with my reflection, only one thing changes, but with a rotation, they have both changed. So this is a rotation. So let's look at those images for a minute and what we just said. A translation, my truck is going the same direction and it's still upright. Okay, so if it's exactly the same, it's just in another location, it just looks like it slid, so that is a translation. If I've either flipped from top to bottom or I've flipped from side to side, that's going to be a reflection. So only one thing has changed. It's either flip from side to side or flip from top to bottom. But notice in number 7, I have 2 changes. Not only has it flipped, but it's also gone side to side, so I can see. So that indicates a rotation. Okay. Let's look at Number 8. It says, use the figure shown where figure QRST is mapped onto figure VWXY. So again, in looking at it, it may be kind of difficult to figure out which letters correspond with each other, but if I pay attention to the order that it's written in, Q is going to correspond with V. Okay, and actually what I'll do is I'll go ahead and put my letters, we'll just do it like that. R corresponds with W. So R and W correspond. S corresponds with X. And then T corresponds with Y. So now looking at it that way, I can see that R and W are together. T and Y are together. But then when I look at Q, what did I do? Oh, Q and V. I was about to call that R, but it looked like a lowercase r. So then Q and V go together. So this is where I notice the change. This is where I notice a difference. Okay. So now if R and T are both in the same place in both figures, but what has changed is V and Q and S and X, then what kind of transformation do I have here? I can see that I've got a reflection. So the pre-image of XY, if I'm looking at, let me erase this real quick. If I'm looking at the pre-image for XY, remember pre-image is my blue. So I'm looking at which one corresponds with XY. Then I know that that's going to be ST. So remember in this one, I would name it as segment ST. Now I'm naming the image of QR. So I'm looking here at QR. The image of QR is going to be VW. Why would I not name that WV? Why would I not name this side WV? Why do I name it VW? Notice here, QR, it starts with Q and goes to R. So I'm going in that direction. I want to make sure that I'm naming it with the corresponding locations. They started with Q, so Q corresponds with V. I want to make sure that if it starts with Q, then the next one starts with V. I want to make sure that I've got my corresponding points, okay? So that's going to be something that we need to be real careful of this next semester. I've been a little lenient on the naming, as long as it worked with the same sides and things like that. I've been okay that if they've been a little bit reverse and things like that, I've still given you credit for it. But now we really want to start focusing on making sure that when we're naming corresponding sides, that everything's going in order. We also want to make sure that you are using the right symbols. So like in this one, remember when I talk about a segment, it's just that line over the top without arrows. It's just a straight line. If it was a line, if we're talking about instead of a segment, we were talking about an actual line, I would need the arrows on the ends, okay? So start paying really close attention to your notation. We'll be working on that as we go through. All right, number 10 says name 2 angles that have the same measure. So if we look at 2 angles that have the same measure, obviously there's 4 angles here. So I could really, I could say angle Q corresponds with angle V. So those correspond. R and W, T and Y, and S and X. Okay, so I can kind of see which ones correspond. And it's totally okay if you need to draw your images and mark them up and write on them to make sure you get everything in the right order. That is just fine. And then it says name a triangle that appears to be congruent to triangle RST. So if I'm looking at triangle RST, I'm looking at this triangle right here, then that means that's going to correspond with triangle WXY. WXY. Whoop. Notice I went from R to S, then to T. So I went WXXY. Any questions? All righty, so we can see on our note sheet, it's about time for our break. So we'll go ahead and look. Our assignment is going to be pages 399 to 400, numbers 13 through 35 odds. Okay, so 399 to 400, numbers 13 to 35 odds. So that is your assignment for 7-1. And we will go ahead and take a 5-minute break and we'll come back and work on 7-2.
Wait, 13 to 35?
Do you have your little paper printed out?
Yes, ma'am.
Okay, do you see at the bottom where it says assignment?
Oh, okay.
Yeah, so it's written right there for you.
Thank you.
Uh-huh. All righty. We'll go ahead and get started back with 7.2. So we were talking about transformations in general, and now we're going to get more specific. And the first one we're going to be talking about is a reflection. Okay, so it says using reflections in a plane. It says one type of transformation uses a line that acts like a mirror with an image reflected in the line. This transformation is a reflection, and the mirror line is the line of reflection. Okay, so in our first part of notes, it says a reflection is a type of transformation A reflection is a type of transformation that uses a line that acts like a mirror with an image reflected in the line. The mirror line is called the line of reflection. The mirror line is called the line of reflection. So a reflection is our first type of transformation, and we've got that line, okay? So we've got two different types of reflections here in our picture. So it says, in a reflection in line M is a transformation that maps every point P in the plane to point P prime. So remember we talked about how when I see that little symbol there, I know that I read that as P prime, and it also helps me to figure out which one is the pre-image and which one is the image. And remember that with P prime, this is which one is the image. Okay, so this is my pre-image. When it's just the letter, my image is the one that has the prime symbol. Okay, so maybe you're not always going to have the color option of blue to red. So if you just memorize it as knowing, so like if it was actually just typed on an assignment or typed on a test and you didn't have the color option, just know that when I see a single letter, that is my pre-image. When I see the same letter with the prime symbol, that is my image. Okay, so that is my mapped image. So we can see that my line, that is my mirror line. My mirror line is running from top to bottom. Okay, but if we look here, so it says if P is not on M, I'm sorry, hold up. Yeah, so it says a reflection in line M is a transformation that maps every point P in the plane to point P prime. So the following properties are true. Okay, so these are the things that I know are true. If P is not on M, then M is the perpendicular bisector of P, of line P, P prime. So M is the perpendicular bisector. So let's stop and think about what that means for a minute. Back in chapter 6, we talked about perpendicular bisectors, or actually it might have been earlier than that. Perpendicular bisector. So remember when I talk about perpendicular, that means that it intersects at a 90-degree angle, and bisector means it cuts it in half. So I know that the distance from my line to P and my distance from my line to P prime are exactly the same. Those distances are congruent because they told us that this is a perpendicular bisector. So I'm still remembering those terms I've previously learned. Perpendicular bisector means it intersects at 90 degrees and it cuts it in half. So I can see that, okay? And then it says if P is on M, if P is a location on line M, then I know that P prime is also a location on M. So P is equal to P prime. So my two things are dealing with if it is not on the line or if it is on the line. If it's not on the line, then I know that that line M is a perpendicular bisector. But if it is on the line, I know that P is equal to P prime. Okay, so let's go ahead and look at example 1, reflections in a coordinate plane. It says to graph the given reflections. So H, 2, 2 is in the x-axis, okay? So let's go ahead and start with 2, 2. We can see that we're starting right here at 2, 2. And then it says G, 5, 4 is in the line y equals 4. So when I look at 5, 4, okay, I'm having to think about this. That remember when we were graphing lines in algebra? And if we said y equals 4, that means that I've got a horizontal line running through y, the point y. Remember, y equals 4 means that 0, 4 is going to be the y-intercept. So that's going to be right here. And I know that I've got a line that's running through horizontally. Okay. So it tells me that 5, 4 is, it says in the line, I like on the line, but anyway, all right. So when I reflect that, I'm just going to stay there and read from my textbook so I don't have to keep moving back and forth. It says since h is 2 units above the x-axis, its reflection h prime is 2 units below the x-axis. Remember, we talked about in isometry, my distance, my length is exactly the same. So if my original point is 2 points above the x-axis, I know that when it's reflected, it's going to be 2 points below the x-axis. And it says start by graphing y is equal to 4. So that's what we talked about just a minute ago. When I see the equation y equals 4, the thing you need to remember is that you've got a horizontal line running through through 0, 4, which is my y-intercept. So I know I've just got a horizontal line that intersects the y-axis at 0, 4. Okay, so it says start by graphing y equals 4, and then you also graph g. So we know y equals 4 and g is 5, 4. So it says from the graph, you can see that g is on the line. Therefore, I know that g prime is also going to be at the same point, 5, 4. Okay, so with the first one, because it reflected over the y-axis, over the x-axis, my x value stayed the same, but my y value changed because it went from top to bottom. Remember earlier when we were going from side to side, it was my x value that changed, but my y value stayed the same. So depending on if it's reflecting over the x value and over the x-axis or the y-axis, one of your values will stay the same and the other will change. So that's what it's telling us right here, is that reflections in the coordinate axes have the following properties. XY reflected over the x-axis becomes x negative y. If XY is reflected over the y-axis, then you have negative XY. So that's just telling you how those change. That may be something that you want to go ahead and add onto your little note sheet, because I did not put that on there. So let me pull that up real quick and we'll add that. So there may be times when we're going through lesson notes and we say we want to add something. So what I'm going to do is, let me pull up right before reflection theorem. Let's go ahead and let's put it right here, right before reflection theorem. And we're going to put if x, y is reflected over the x-axis, the image is point x negative y. So if it's reflected over the x-axis, the image is going to be x negative y. And then if x, y is reflected over the y-axis, the image is point negative x, y. So the key there to determine which point will be positive and negative depends on which axis it is reflected over. So this is from page 404, right above that green box that says reflection theorem. We're going to add that little note in there. All right, so our next little point says a reflection is an blank because the length of the segments is preserved. And so that is going to be an isometry. So that is going to be on page 404 right at the bottom. Let me go back to the text. Okay, so we just added those notes. And then theorem 7.1 says reflection theorem. And it just says that a reflection is an isometry. So I can automatically assume that whenever I hear that a reflection is an isometry, then I know that my lengths are exactly the same. I know that nothing is changing about that. Okay? So I know the lengths are the same, my angles are the same. What else did we say was the same? Lengths, angles, distances. Let's flip back. I'm losing my words. Lengths, angles, parallel lines, distances between points, all that stuff. So if parallel lines in one, it'll be in the other. All right, so now we're going to flip over or look at the top of page 405. So it says that if we wanted to prove the reflection theorem, I would need to show that the reflection preserves the length of a segment. Excuse me. I would have to show that my lengths are exactly the same. So if we look at case 1, and I look at PQ, and then P prime, Q prime, I would have to be able to prove that from P to Q is the same length as from P prime to Q prime. And that from P to P prime is the same length as I'm sorry, I said that wrong. That PQ, the length of PQ is congruent to the length of P prime Q prime. Case 2, I have P and Q on opposite sides of M. So I can see the reflection, the line of reflection is M. So I would have to see that my distance are the same there. Notice in case 3, we have P that is lying on M. So we just talked about a minute ago that if my point is actually on the line, then we know that they are equal. And then my point Q is off the line and Q prime is off the line. So my distance from Q to M and the distance from M to Q prime would be the same. And then case 4, Q is lying on PQ, but then we can see that line PQ is perpendicular to M. And so I know that my distance from P to Q is going to be equal to the distance from P prime to Q prime because it's a perpendicular bisector. Okay. So example 2 says if we wanted to prove case 1 from theorem 7.1, if I wanted to prove that, it says I'm trying to prove that PQ is equal to P prime Q prime. So on this, basically, it just says for this case, P and Q are on the same side of M. So you would draw line P prime, and our segment P prime, and segment Q prime, intersecting at line M, and then R and S, those are those intersection points, and then draw RQ to RQ prime. By the definition of a reflection, M is perpendicular to segment Q prime, and segment QS is congruent to segment Q prime S. It follows that triangle RSQ is congruent to triangle RSQ prime using the side angle side congruence postulate. Therefore, RQ is congruent to RQ prime, and angle QRS is congruent to angle Q prime RS.
because line RS is a perpendicular bisector of segment P prime, you have enough information to apply the side angle side to conclude that triangle RQP is congruent to triangle RQ prime P prime. And so it says, because corresponding parts of congruent triangles are congruent, then PQ is equal to P prime Q prime. Okay, so again, understanding why these are congruent. Again, I'm not focusing so much on the order and things like that a proof goes through. My main thing is that you can look at the diagram and understand that what you're seeing, that you can see, we've got the triangles drawn, we've got our perpendicular bisector, which is line M. Therefore, my distance from P to my line and from my line to P prime are going to be congruent. And they just put that point R to show that that's where it's between. Then they've put point S to be the midpoint between Q and Q prime. And so again, understanding that the perpendicular bisector cuts it in half, that means either side is congruent. So therefore, if we were to put measures in here, let's say that I said that distance is 12 inches. Therefore, if I know that that side is 12 inches, I know this side is 12 inches because they are congruent. Or I said inches. Yeah, there we go. Then by understanding that it's a perpendicular bisector, by understanding that it's cut in half from P to R and from R to P prime, I could go ahead and label these if I had numbers to be able to label it by understanding those definitions. Okay, so we're not only taking that understanding, later on we're going to be expanding on it by being able to look at measures and understanding what they would be based on our definitions. All right, example 3, finding a minimum distance. Surveying, 2 houses are located on rural road M, as shown on the right. You want to place a telephone pole on the road at point C, so the length of the telephone cable, AC plus BC, is a minimum. So they're putting up a pole. They want the line to be as short as it can be. And so it's saying, where would you locate C? So think about the shortest distance between 2 points is a straight line. So what you're looking at is you're looking at where would we need to put that. So it says reflect A in line M to give A prime. Then you would draw segment A prime B, label the point at which the segment intersects line M as point C. And because A prime B represents the shortest distance between A prime and B, and AC equals A prime C, you could conclude that point C, a minimum length of telephone cable is used. So basically going from here to here, here to here would be our shortest distance, okay? Now goal 2, moving on, reflections and lines of symmetry, okay? Did I skip over? No, we already did that one. Okay. A figure in the plane has a line of symmetry. If the figure can be mapped onto itself by a reflection in the line. So a figure in the plane has a line of symmetry if the figure can be mapped on itself by a reflection in the line. So your blank there is as a reflection in the line. So basically we're saying here that our line of symmetry is our line here that we are using as our, I'm losing my words today. It's our line of reflection. So a line of symmetry, it is a line of symmetry if it is a line of reflection. So it says hexagons can have different lines of symmetry, but depending on their shape. So remember, a hexagon is just as a six-sided figure, okay? But they're not all drawn exactly the same way. We can see 3 different pictures here of a hexagon, okay? So letter A, I have a 6-sided figure. 1, 2, 3, 4, 5, 6. But the only line of symmetry that I can see here is going from top to bottom. Okay, so I can see that everything is exactly the same on the left side of my line of symmetry or line of reflection as it is on the right-hand side. Look at letter B. Again, I could not put this as a line of symmetry because notice this is not exactly the same. So what we notice here is because I've got angle differences, okay? If I were to draw a line of symmetry there, my angles do not match up right. My lengths may, but my angles do not. But when we have what's called a regular hexagon, remember a regular hexagon means that all of my sides are exactly the same, all of my angle measures are exactly the same, then we can see all these different lines of symmetry going from vertex to opposite vertex. So lines of symmetry depend on the shape of the object. Okay. So just because it's a 6-sided figure doesn't mean that every single 6-sided figure is going to be exactly the same. Example 6, identifying reflections, and it talks about a kaleidoscope. I don't know about you guys, but if you've ever looked through a kaleidoscope, surely we've all been able to look through one at some point. How fun it is to shine it up at the light and then turn it and watch how all those things move around. But in the kaleidoscope, you're seeing reflections because it's made up with a system of mirrors in there. And so the way that when you turn it and the mirrors move and it reflects the object, it's reflecting and showing us patterns of symmetry. But the number of lines of symmetry depends on the object. So it says inside a kaleidoscope, 2 mirrors are placed next to each other to form a V, as shown at the right. So we can see where we have the 2 mirrors where they kind of meet at point A. And so it says the angle between the mirrors determines the number of lines of symmetry in the image. The formula below can be used to calculate the angle between the mirrors A, or the number of lines of symmetry in the image, which is N. So A is the angle between the mirrors. So whatever the measure of that angle is. And then N is the lines of symmetry in the image. So basically, I'm going to multiply my number of lines of symmetry in the image by whatever the measure of the angle is. And then that tells me what I've got. So if we look at letter A, okay? Look at letter A. It says use the formula. The formula I'm using is right up here. N times the measure of angle A equals 180. So it says use the formula to find the angle in the mirrors that must be placed for the image of a kaleidoscope to resemble the design. So let's think about this for a minute, okay? I know that my lines of symmetry, I know that I'm dealing with congruent measures. So, okay, so if we think about from here to, well, I'm gonna do a different color so it'll stand out. If I'm looking at this angle measure here, what do I know the degrees of a straight line is? It's gonna be 180 degrees, right? And I can see that it's broken into 3 congruent parts. So that means that this is 60 degrees, this is 60 degrees, this is 60 degrees. Therefore, if I have 3 lines of symmetry, 3 times the measure of angle A equals 180, because 180 divided by 3 is 60 degrees. Okay. On here, I've got 4 lines of symmetry. Again, I've still got my 180 degrees, but it's broken into 4 parts. So 180 divided by 4 is 45 degrees. So I can see that this is 45, 45, 45, 45. And then finally, letter C, I've got 6 that make up that 180 degree. Divide by 6, divide by 6, I can see that I've got 30 degrees, 30 degrees, 30 degrees, 30 degrees, 30 degrees, 30 degrees. Any questions on that? So basically, by looking at my lines of symmetry, depending on the number of lines, I can figure out what each of those angle measures are by looking at the numbers of lines of symmetry. All right, so moving on to guided practice. So if we talk about what a line of symmetry is, basically our line of symmetry is going to be whatever that reflection line is, whatever line I'm using to show a mirror image from one thing to the other, and that a line of symmetry and a line of reflection are going to be the same. And it says when a point is reflected on the x-axis, how are the coordinates of the image related to the coordinates of the pre-image? So for that, we're looking back on page 404. That little note that we added to our note sheet. If it's reflected over the x-axis, my image is going to have a negative y value. Or actually, let me say this, it's going to have an opposite y value. Because what if you started out, what if your pre-image was, what if your pre-image was 2, -3? Then your image is actually going to be 2, 3. So just know that just because I'm starting with both positive and going to where y is negative, understand that that's going to mean it's going to be the opposite of y. So if it started out as a negative, if the pre-image is a negative, then my image will be positive. Okay? But if my pre-image is positive, then it flips to negative y. But just know that we're taking the opposite of y. So what I'll do here, if you want to go ahead and add that note, opposite of y. Because if it starts out as a negative, it's going to turn positive. And then the same thing here, the opposite of x. Because if x starts out negative, then its image is going to be positive. Does that make sense? Any questions about that? Just understand that this is not saying that the pre-image or that the image will always have a negative y, or that the image will always have a negative x if it's over the y-axis. All righty, so going back to number 3 on page 407. It says to determine whether the blue figure maps onto the red figure by a reflection. All right, so look at 3. If we look at number 3, do I have a reflection there? I don't, do I?
You have what's called a translation?
It's a translation. Yeah, it just looks like it slid right over that line. So that is not a reflection. Now let's look at number 4. Okay. On number 4, could this be reflected over line M? Think about if it was going to be reflected over line M, then it's still going to be like that. Okay. It's still going to be, but in this one, this would actually be a rotation here, because if it was just flipped right over, I'm still going to have that arc in the top. It's just that this point would now correspond with this point. Okay, so that is not a reflection either. Look at number 5. This is a reflection because we can see that this point corresponds with this point, this one with this one. We'll do a little star here, this one with this one, and then that one with that one. So I can see my lengths, my corresponding lengths are going to be congruent, and everything is in the correct location if it reflected over that line. All right. Now it says use the diagram at the right to complete the statement. I'm looking at AB maps to what? So I'm talking about AB right here is going to map to EF. Okay, so if we go through any of these and you have a question, be sure to let me know. AB maps to EF. The next one says, number 7, what maps to DEF? So if I'm at DEF, then that is going to be angle DAB. Okay, and we said the first one was AB went to EF. Okay, like I said, this is the point where we're trying to be real careful about our symbols that we're using. Notice that when I said EF, I didn't just write EF. I went ahead and wrote the segment line over it. Also, when I was talking about angle DAB, I've put my little angle sign in front of it. All right, look at number 8. Point C reflects to point G. So C reflects to G. Look at D.
M.
Okay, so look at D and M. Notice M is that lowercase italic, so that's just naming it, whereas D is a point on the line. Remember that we talked about if we don't see a differentiation there, if we don't see and actually D is on the line, then it is just equal to itself, okay? Because it is a point on the line, because point D is going to be right there, then D is equal to D. Okay, it's just equal to itself because it's just flipped right there. Okay, now look at 10. I'm trying to see which one became angle GFE. So let me change my color real quick. And I'm going from G to F to E. So if I'm going from G to F to E, I'm looking at where I would have started on the other one, and that would be from C to B to A. So that would be angle CBA. And then number 11, what translated to DG? So DG right here, I've got a mess. Let me erase this so we can see better. Okay, so DG is going to be DC. DC reflected to DG. Any questions on that? All right, and now we're looking at our lines of symmetry and our flowers. Look at number 12. Okay, determine the number of lines of symmetry. So notice that, let me get a different color. Notice that if I had a line going straight through that way, I've got a mirror image. So if I had one going straight through that way, I've got another one. And then straight through that way, I have another one. So I can see my 3 lines of symmetry. How many lines of symmetry do we have in number 13?
Would that be 2?
Okay, let's look at it. So with this one, not only would I be able to go that way and that way, but I could
That'd be
also go
4.
through here. Yeah. And I can go through here. Okay. And then let's look at number 14. How many lines of symmetry would I have here? I could go this way and have 1, this way and have 2, 3, 4, 5. Now, one of the things I want you to notice is how do the number of petals correspond with the lines of symmetry? Look at the yellow one. It has 3 petals and it had 3 lines of symmetry. Number 13 has 4 petals, 4 lines of symmetry. 14 has 5 petals, 5 lines of symmetry. Okay. All righty, so you can see our assignment for this section is going to be pages 407 through 409. We have numbers 15 through 29 odds, and then we jump to number 49. So go ahead and flip over and let's look at number 48 together. Okay, so page 409. Let's look at number 48 together. So we are actually applying algebra now to our shapes. And so because we understand that with a reflection, we have congruence from one figure to the other. Remember, congruence means equal to. So therefore, I'm able to apply these different things. So if I look at this right here, first thing I'm going to do is I want to solve for x. So I can see that this is congruent to this. Therefore, 3x is equal to 4. So I can set up an equation where I have 3x is equal to 4. Divide by 3, divide by 3. So x equals 4/3. That's all we do. Okay? If I'm looking to solve for y, I can see that this side is congruent to this side. Therefore, 1/2 y minus 10 is equal to 8. Add 10, add 10. 1/2 y is equal to 18. Remember, if I have a fraction that I need to get rid of, a fraction is a type of division problem. To undo division, I multiply. So I'd multiply both sides by 2. Those cancel out. So y is equal to 18 times 2 is 36. And then finally, I've got this side is congruent to this side. So 2z minus 1 is equal to 5. Add 1, add 1. 2z equals 6, divide by 2, and z equals 3. So I was able to solve for x, y, and z by looking at what sides correspond with what sides and setting up an equation to say this is equal to this. So that's what you're going to do in number 49. You're going to look to see what sides correspond with the other based on the reflection and set up an equation and solve. Okay, that's all you're doing there. Any questions about that? All righty. So that wraps us up for today. So you can see from your assignment sheet or from your lesson notes that from 7-1, our assignment was pages 399 to 400, numbers 13 through 35 odds. And then for 7-2, our assignment is page 407 to 409, numbers 15 through 29 odds, and number 49. Any questions about that? All righty. Well, I will try to send out the note sheet much earlier than I did last night. But I'll get our note sheet together, and I will send you the new link for tomorrow's class for our Thursday classes. So be looking for an email from me. Hopefully I'll get it done in just a few minutes. I should be done with that. I'll go ahead and work on that immediately right now to get that to you so you have time to print it for tomorrow's class, and then also have the link. So be looking for that email. If you have any questions between now and then, please be sure to let me know. But if not, then I will plan on seeing you guys in the morning.
Bye, Miss Jennifer.
All right, bye. See y'all tomorrow.
Bye, thank you.
Bye. Thank you, hon. Let me know if you have questions. And Clara,